Thank you very much, Ivan. Thank you so much for this welcome address. What I would like to do is now to hand over to the first session chair, and that's David Belshon. Oh, I can see David already. Hello. So you're unmuted, and yeah, okay. So yeah, we can all see you. So so great.
Video, right?
Yes. And the first speaker is Henning Sirringhaus.
Okay, so good morning or good afternoon, whatever applies. We have an excellent really lineup of speakers today, talking about charge transport in organic materials, and both from an experimental side and from a theory side. And as always, us theoreticians are very much inspired by experiments. And so the first talk would be given indeed by Henning about charge transport in molecular semiconductors. So Henning, the mic is yours.
Thank you very much, David. Are you able to see my screen?
I do.
Good. Thank you so much, Jochen, also for the kind invitation. It's taken a while to actually it happen, but I'm very glad that this event is finally going ahead and we can enjoy each other, the interactions with each other over the coming days. I want to talk to you about charge transport in organic semiconductors, specifically high mobility organic semiconductors. And because it's the beginning of the conference, let me just motivate this a little bit by showing you an overview over some of the applications of organic semiconductors. Of course, there are now many, going all the way from the more kind of established applications like organic light emitting diodes, organic solar cells. There's a lot of interest also now in bioelectronics, flexible electronics. There's a whole range of very interesting applications for organic materials. And of course, there's many physical processes, physical properties that need to be really understood at the fundamental level to make these applications happen. And the one that I want to focus on in my talk is the charge transport physics of these materials. And of course, charge transport is relevant for all these applications. And what of course has happened in this field over the years is this incredible interplay between physics, chemistry, material science, the exploration of different molecular structures, both small molecules and polymers, and then understanding what's actually needed for the application, what's needed, for example, to boost the carrier mobilities of these organic semiconductors. That's been an incredibly successful program and has led to several orders of magnitude improvements in the key figure of merit of charge transport, which is the carrier mobility of these materials. And I want to focus in this talk on three main subjects. I want to give you an overview over how we understand the charge transport physics of both molecular semiconductors, crystalline molecular semiconductors. I want to talk about conjugated polymers, where we now have materials that achieve similar carrier mobilities as the small molecule systems. And of course, the polymers tend to be much more disordered structures, so there's a somewhat different transport physics to be understood here. And then in the third part of the talk, I want to talk a little bit about conducting systems, so conducting polymers in which we have a very high doping density, where the carrier concentration is approaching the molecular density on the order of 10 to the 20 to 10 to the 21 per cubic centimeter, and understand how transport can be described in these systems. But let me start with a very simple view of the molecular electronic structure of a molecular semiconductor. Of course, if you start with the molecular orbitals of the basic molecular units, I've shown here the molecular orbitals of benzene. Of course, you can do similar calculations, similar predictions also for more complicated molecular systems. And then if you try to based on that, you understand the electronic structure of the bulk solid, the molecular crystal, then you would typically expect there to be some form of broadening of these molecular orbitals due to the interaction between the individual molecules. And if you are a solid state physics physicist, you would then be able to draw a band structure, and that's shown on the bottom right, the band structure of pentacene. And kind of, it looks relatively boring. You typically have these very flat bands where there is very little band dispersion. And the reason for that is that the intermolecular interactions in these molecular crystals tend to be relatively weak because the distance between the individual molecules is 3 to 4 angstroms typically. And that means that the transfer integrals that reflect these interactions tend to be relatively small, and so the bands are flat. And so if it was only this that was happening, then organic semiconductors would of course be incredibly boring, much less interesting than many inorganic semiconductors, where you can get much stronger interaction effects and more interesting band structures. But if you actually look at the physics of transport of organic semiconductors from an experimental point of view, there's a lot of interesting features that can't be easily understood within this conventional band structure picture that we have from inorganic semiconductors. On the one hand, you have transport signatures that are very reminiscent of inorganic semiconductors. You have, for example, in the temperature dependence of the mobility, I show you on the top left, the temperature dependence of the mobility of a rubrine molecular crystal, one of the most widely studied systems, from the beautiful work of Vitalo Podzarov, whom we're going to hear from later this week. And you can see here that at room temperature, the mobility is moderately high, a few centimeters squared per volt second, but then as you cool down, the mobility increases with decreasing temperature. And that's somewhat reminiscent of some scattering physics, where as you cool down, the scattering mechanism with phonons is becoming less effective, and mobility increases. You also can measure the Hall effect in these systems. And it turns out that in many systems, the Hall effect shows an ideal signature where the Hall resistance is inversely proportional to the carrier concentration. But if you then look at other transport signatures, there are things that are not so easily understood. And we have done a lot of work in my group on the optics of charges in these molecular semiconductors. And very briefly speaking, if you basically measure the optical absorption spectrum of a charge carrier in an organic semiconductor, the optical spectrum looks very similar to the spectrum of a charge that would be on an individual molecule. For example, you can do that very easily, that experiment, measure the absorption spectrum of charged molecules in solution. Often the solid state spectrum looks very similar to that, and that would suggest that the carriers are actually quite localized and have a rather molecular nature, as opposed to the kind of Bloch electron picture that we have for inorganic semiconductors. And then you can look at other signatures, and I've again shown here an example from Vitali's work here, who's looked at the strain dependence of the carrier mobility. And what you typically see, that relatively small amounts of strain can give rise to very large changes in carrier mobility. And that's also something that it's not easy to understand within a band structure diagram, where you kind of maybe look at how the effective mass might change with strain. It requires really a different physical picture to understand some of these observations. And of course, one of the reasons why that might be is because, of course, one of the features of organic semiconductors that's quite unique is the soft intermolecular interactions between molecules. So if you look at the bonding between molecules, that's a soft van der Waals interaction. And that necessarily leads to relatively large thermal lattice fluctuations. You can see that manifested here in this view graph on the top left. You see an electron diffraction pattern of a molecular crystal of TIPS pentacene, the molecule that you see here in the center. And in addition to the sharp diffraction spots that you can see here, you can also see these diffuse streaks in the diffraction pattern, and they reflect the thermal lattice fluctuations that you have, those displacements of molecules with respect to each other in the unit cell, they give rise to these diffuse streaks in the diffraction pattern. And we've developed a model that allows us to refine these diffraction patterns and extract the amplitude of these molecular motions. And what you find is that at room temperature, there's about several tenths of an angstroms lattice fluctuations of molecules moving against each other in the unit cell. And if you ask yourself what effect that has on the electronic structure, on the charge dynamics, of course, you need to, you realize that actually small displacements of molecules relative to each other, they would change the transfer integrals. You can see that plotted here on the top bottom right. It's a plot of how the transfer integral between two tetracene molecules changes as you shift the two molecules along their long molecular axis. And you can see here that small shifts of the relative position of two molecules can induce quite large differences in the transfer integrals. There are points where the transfer integral is very small, almost zero. Then there are points where the transfer integral is maximum. So if you have now these thermal lattice fluctuations, they basically lead to strong fluctuations, temporal fluctuations of the transfer integrals. And that is the key, in our view, that's the key feature that governs the charge dynamics in these molecular crystals. And that was theoretically, of course, we will hear a lot more about this later in the week, but I can't resist to show you two very pioneering pieces of theory on this system. So first was done by Alessandro Troisi and also Simone Frattini, who is also going to speak later in the week. And so Simone's group developed a framework for understanding how charges move in such a fluctuating lattice with thermally fluctuating transfer integrals and site energies. It essentially gives rise to a localization of the carriers on a kind of typically 10 picosecond or so time scale. The charges, they see a disordered landscape, they localize within that disordered landscape, form localized electronic states. But then on a longer time scale of timescales, maybe of hundreds of picoseconds, you have an evolution of that disordered lattice. And with that structural evolution of the lattice, the charges then start to diffuse, and they're essentially surfing on the waves of molecular lattice distortion. That's at least a kind of simple intuitive picture in which you can understand this. The electrons are moving in response to the structural lattice evolution. And there's a beautiful visualization of this process in the work that Jochen published 2 years ago, which captures very similar physics. What you can see here are view graphs of the electron wave function in a molecular crystal on the bottom right. So 3 different snapshots of the wave function in a molecular crystal. And what you can see there is that there are moments in time where the wave function is rather localized at 162 femtoseconds, we have a rather localized state. And then just 30 femtoseconds later or so, the wave function is much more delocalized. And then a little bit later, the wave function is back being localized again. But necessarily, it doesn't localize in the same region that it started in. And so there can be long-range charge transfer by this mechanism. And so that's the process that governs the diffusion of charges and that ultimately governs the carrier mobility. So this is a really beautiful visualization of how we understand charge transport in this kind of dynamically localized systems. This has now been taken a step further, and of course we are ultimately interested in understanding carrier mobilities within this so-called transient localization, or sometimes people call it transient delocalization regime. The mobility can be expressed in terms of 2 key quantities. One is this localization length over which the electrons are able to delocalize in this dynamically disordered lattice. And then the other key quantity is the characteristic vibration time, or the characteristic vibration frequency. And if you know these 2 quantities, you can compute the carrier mobility. And the localization length depends on a number of key parameters. It depends on the distribution of transfer integrals. Turns out, and I'm sure Simona will tell us more about this later, that it's best if the transfer integrals are isotropic and the different transfer integrals in different directions are of similar magnitude. You want the thermal disorder, these fluctuations of the transfer integrals, I've labeled them here, delta JA over JA. That's the relative fluctuation of the transfer goal, let's say in the A crystalline axis. You want this dynamic disorder to be as small as possible. And then also you want the molecular frequencies, omega naught, the characteristic vibration frequencies, you want them to be relatively high so that this dynamic evolution of the lattice happens quickly. And if you take these three factors into account, you can predict mobilities quite quantitatively. And you can see that here, a plot of theoretical mobilities and experimentally observed mobilities in single crystals. And there is a reasonably good agreement between what the theory predicts and what we observe experimentally. And there are, of course, kind of more detailed factors that need to be taken into account. I don't have time to discuss that in detail. We have been particularly interested in understanding not just the effect of vibrations in aggregate, but look actually mode by mode, what the effect of individual vibrational modes is on the thermal disorder. Of course, there are hundreds of modes because the unit cells are large in these molecules. And so you can ask yourself, individual mode by mode, what does each mode contribute to the electron-phonon coupling? And to our surprise, when we analyzed this particular system, which is called DNTT, it's a fused thiophene phenylene system. And then we can attach side chains, in this case C8 side chains in the molecule on the right here. And what you can see here is how the dynamic disorder, the thermal disorder in the transfer integral builds up as we go from very low frequency modes, the intermolecular modes, go all the way to higher frequencies, moving towards the intramolecular modes. And what's interesting here is that this goes in steps. I mean, there are certain modes that contribute a lot to the thermal disorder. In the C8 DNTT case, for example, there seems to be a single mode that contributes about 70% of the dynamic disorder. And so that's an interesting observation because it opens up the possibility, at least, for molecular design rules. If there is only certain modes that don't generate most of the disorder, we can try to tweak these modes by molecular design and try to reduce the electron-phonon coupling that's associated with these modes. And we're starting to develop such design rules, and hopefully that will help us to identify molecular systems that have even higher carrier mobilities. I should maybe mention in passing that we're not just interested in charge transport, we're also interested in thermal transport, heat transport in these systems, because in my group, I've also got an emerging interest in thermoelectric applications of organic semiconductors. And I show you here on the very same molecules, DNTT and C8 DNTT, that's also the thermal transport is very sensitively affected by these attachments of these alkyl side chains. And for the C8 DNTT molecule, we see very low thermal conductivities. At room temperature, the thermal conductivity in a polycrystalline film of this material goes all the way down to 0.05 watts per meter Kelvin. That's one of the lowest values that's been measured in kind of any solid material. And we're starting to understand also where that comes from. This is a collaboration with Jérôme Cornet's group in Mons. They have calculated the thermal conductivity in these systems. And it turns out that the reason for this strong suppression of the thermal conductivity is the fact that the attachment of the alkyl side chain lead to a much stronger localization of the vibrational modes. So in the unsubstituted molecules, the vibrational modes are more extended over a larger number of molecules, and the attachment of the side chains tends to localize these phonon modes. So there's interesting features of this structural dynamics also in the thermal transport properties. I now want to switch over to the polymer systems. And in polymers, of course, we have a slightly different problem in the sense that a conjugated polymer is never a single crystal. You typically have to deal with kind of ordered domains where maybe there is some crystalline arrangement of the polymer chains with respect to each other. But then you also have more disordered regions where the chains are more amorphous, with less close packing and stacking between the polymer chains. And so in addition to the dynamics that's been the focus of our work in the molecular systems, we also have to worry here about more static disorder effects. But even if you have a kind of statically disordered landscape in which you can maybe generate or think about what might be the eigenstates in which the electrons would localize within such a disordered landscape, you need to worry about the dynamics, because if the lattice was completely, if such a lattice of polymer chain was completely static, there was no dynamics, then the electrons would just sit in their eigenstates happily, and they wouldn't really move between eigenstates. And so it's believed to be that dynamical coupling, the vibrational modes, the torsional modes of the polymer backbone, that basically mediate the coupling between the eigenstates. So the dynamics is also relevant in these systems. I just want to show you quickly, just to give you an idea of the kind of systems that we are working with. So this is a polymer system that we discovered a few years ago. It's one of the highest mobility conjugated polymer systems that we have. So it's a polymer that we call IDTVT. It's quite an interesting system in the sense that it's a pretty amorphous, or not completely amorphous, but it's a pretty disordered system where there is only very little evidence for pi stacking. In the X-ray diffraction, there is very broad diffraction peaks, and so it's but still, nevertheless, we are able to achieve quite high carrier mobilities, up to 3 centimeters squared per volt second in this system. We typically see in these systems not a band-like temperature dependence of the mobility, but a thermally activated temperature dependence. That's quite typical for polymer systems. We're also working on other systems. This is a more recent example here from work that we're doing together with Ian McCullough's group, now in Oxford. And this is a system where we have quite a unique backbone structure. If you look at it, we have some rigid units along the polymer backbone, and then they're coupled to each other not by single bonds, but by double bonds. And that makes for a more rigid polymer backbone structure. Of course, it makes also the units more strongly coupled to each other. So we need to be particularly careful in these systems to organize them well enough so that we kind of reduce structural disorder as much as possible, because any torsions, for example, along the backbone would lead to quite large energetic disorder because of that strong coupling. But we are starting to be able to do this, and we now have quite interesting, or starting to have quite respectable carrier mobilities in these strongly coupled systems, and carrier mobilities reaching up to 1 centimeter squared per volt second. Very briefly, I wanted to talk about how this kind of dynamics, this dynamical evolution, structural evolution manifests itself in the transport properties of these polymer systems. It's not so easy to observe because in the temperature dependence of the mobility, as I said, it's usually activated. And so you're never quite sure, is that thermal activation due to static energetic disorder, or might it have something to do with the dynamics? But we've looked at other transport properties. In particular, we've looked at the spin relaxation physics of these polymer systems. And I don't really have time to discuss it in very much detail, but near room temperature, we see a regime in the spin relaxation of these polymers where, with increasing temperature, the spin relaxation times decrease. And that's a little bit unexpected, because you would normally expect spin relaxation to become less effective as the carriers become more and more delocalized. As they move faster and faster, normally spin relaxation becomes less effective. But in these systems, spin relaxation becomes stronger as we increase the temperature. And we think that that process is a process that reflects the dynamical coupling of the electron wave function to the structural dynamics. You can see here some simulations from the chairman of our session, David Beljon's group, who simulated the carrier wave function sitting on a polymer chain here. And at different points on the picosecond timescale, you can see how the electron wave function moves back and forth along the polymer backbone. And that motion, rapid motion, oscillatory motion along the polymer backbone is driven by structural vibrations, by torsional dynamics. And these torsional motions, they in a sense, it's a bit similar to what I've explained with the molecular systems. The electron wave function is here also surfing on the kind of waves of vibrational created by those vibrational modes, the torsional modes in this case. And we think that it's this rapid oscillatory motion along the polymer backbone that is basically providing this mechanism for spin relaxation. As temperature increases, this becomes more and more active, and the finite spin-orbit coupling that's present in these molecules then provides a mechanism for spin relaxation. So this is a probe for us to actually probe this rapid dynamics on a kind of molecular scale using the spin relaxation. And what I find quite remarkable is if you compare this behavior to the molecular system, to the molecular crystals, I show you here a comparison between the spin relaxation of a molecular crystal on the top from Juntakea's work, and on the bottom is the our measurements of spin relaxation in the polymer system. And although the temperature dependence of the mobility in these two systems is very different, in the molecular crystal, you see this band-like drop of mobility with increasing temperature. And in the polymer, you see the thermal activation where the mobility increases with increasing temperature. Despite of that, the spin relaxation times of these two systems are pretty similar. They're all, in both cases, on the order of 100 nanoseconds near room temperature. And they also, both of them show this regime that I talked about, where the spin relaxation becomes more and more efficient near room temperature as the temperature increases. And we think that it's a reflection, this very close similarity of the spin relaxation behavior is a reflection of this close coupling between the structural dynamics, the charge dynamics, and the spin dynamics. And we think that's very similar on a molecular scale in the polymer systems and in the molecular systems. I have another few minutes left now to talk very briefly about transport in conducting polymers. And of course, in these systems, we have, as I said, a very high carrier concentration that's present because we want to achieve high conductivities. And typically, we dope these systems to carrier concentrations on the order of 10 to the 20 to 10 to the 21. And then you have to worry not just about static disorder, the static disorder that's generated also due to the dopant incorporation. You have to worry about the dynamic effects, but you also have to worry about the Coulombic effects. The carriers interact with the dopant ions by Coulombic interactions, and they also, of course, interact with each other by Coulombic interaction. So it's a much more complicated systems. And we have started to try to understand how this physics, how this coupling between these different factors works in such systems. And for this, we use I maybe should not explain in too much detail. We use a doping technique, which we call ion exchange doping, which was developed by Juntakea's group a few years ago. So we using this technique to basically dope these systems in a very controlled way. So the way this technique works is that you use a molecular dopant to induce an electron transfer on the surface of the film in solution. But then what gets in, you do this in the presence of an electrolyte, an ionic liquid. And then what gets incorporated into the film is the ion of the ionic liquid. So there's an ion exchange on the surface. And then you have basically a doped film in which you have mobile charge carriers on the organic semiconductor, on the conjugated polymer. And then they are balanced by counterions that are essentially closed shell ionic liquid ions, which we can select from a very wide range of ions. So in particular, we can now study how the charge transport depends on the shape and size of the counterion. And with that, we can tune the strength of the Coulombic interaction between the mobile charges on the polymer and the counterion. And so this technique works very well. We can get very high levels of doping. We can completely bleach the neutral absorption of the polymer when we dope to such high levels. We quantify the carrier concentration using a range of techniques and verify that we indeed get into this very high doping regime. And in this system here, PBTTT, polythiophene-based polymer, we get to doping concentrations of 8 times 10 to the 20 per cubic centimeter. We know the structure. So this is some simulation from David Beljon's group, refined against experimental X-ray diffraction measurements. So you can see here how these counterions get incorporated into the polymer lattice. You have this characteristic lamellar structure, the PBTTT backbones, you can see them here. And then you have a lamellar structure with interdigitated side chains. And there is this space in this interdigitated side chain region here where those dopant ions, the ionic liquid ions, get incorporated. And then by changing the size of these ions, you can tune the distance between the charges on the polymer backbone and the position of the counterions. And so then we've played around and varied the size of those counterions from very small ions, like PF6 is a very small ionic liquid counterion, all the way to this very large counterions. BARF is one of the largest ions that we've looked at. And we've tried to understand what actually is conductivity correlated with. Is it the ion size that matters? We had thought initially, if we went to small ions, we would bring the charges and the counterions closer together, and that would tend to, of course, increase the Coulombic interaction. And it turns out that in most of the systems that we've looked at, there is actually not much evidence that ion size is very closely correlated with achievable conductivity. It's rather something else that we found to be closely correlated with conductivity, and that's the so-called paracrystallinity. The paracrystallinity is a measure of the quality of the crystalline order. So the paracrystallinity measures the variation in the pi-pi stacking distances. And so if you have a large paracrystallinity, then you have a more moving towards an amorphous structure, and a small paracrystallinity is essentially moving towards a more ordered system. And so we've looked at a number of systems. I don't have the time to discuss it in detail. We have looked at P3HT. We've looked at some donor acceptor systems like this polymer DPPBTZ and IDTBT. And to summarize, what we found is that, in fact, the conductivity seems very closely correlated with the paracrystallinity. So we see for paracrystallinities below 10%, we are able to achieve very high charge carrier conductivities up to 1,000 Siemens per centimeters. And then if we go to higher paracrystallinities, tens of percent, then the achievable carrier conductivity drops by orders of magnitude, and you can see that in this slide here. And I want to close by some theoretical work that we've done to understand why this happens. And so this is some work done by Gabriele Davino in Grenoble, working together with Simone Frattini. And Gabriele has built a very interesting model, Hamiltonian, for such conducting systems. You can see how this is a picture here illustrating this Hamiltonian. So it's a network of sites. In the X direction, you have essentially the polymer chain direction. And in the Y direction, you have, it's for a semi-crystalline polymer. So in the Y direction, you have essentially the direction of pi-pi stacking. You can see that these chains are not all stacked with the same distances. So there's some variation in the pi-pi stacking distances incorporated into the model. So that's reflecting the paracrystallinity. And then we have a network of counterions. These orange blobs are the counterions, and we place them just above and just below a two-dimensional plane of these conjugated chains. And then we parameterize this Hamiltonian in the best possible and most accurate way that we can. So we calculate the transfer integrals from first principles. We even take into account how the transfer integrals might change with paracrystallinity, because of course, as you expand the crystalline lattice, you might induce some torsions in the backbones. And so the model takes that all into account and tries to build an as realistic model as possible of the electronic structure as a function of the packing and the crystalline structure. The model takes into account the dynamic effects. It takes into account the Coulombic interactions between the carriers, the Coulombic interactions between the carriers and the dopant ions, and then calculates the conductivity within the same transient localization framework that I've discussed earlier for the molecular single carriers in molecular systems. So it uses a relaxation time approximation to take into account that the lattice evolves dynamically on a characteristic timescale determined by characteristic vibration frequency. And in this model, we can then calculate the density of states. We can calculate the delocalization lengths of the carriers, and we can calculate conductivities. And what's interesting here is that there seem to be two main factors that limit conductivity in this system. One factor that doesn't limit conductivity is the dopant distance, so how far the dopants are away from the conjugated planes. That doesn't seem to affect either localization length nor the conductivity very much. And that's of course because in these systems the carriers are sufficiently delocalized that they essentially average over these individual Coulombic wells that might be formed by those dopant ions. So that is not a factor that we worry very much anymore about. But what seems to be limiting the conductivity is the paracrystallinity. And you can see below a plot of the electrical conductivity as a function of paracrystallinity, and that reproduces very beautifully the experimentally observed data, not just qualitatively, but also quantitatively. And then the second factor that seems to be important, if you look at the density of states plots on the left, you can see that, so you see the band here, of states, and then at the Fermi level at zero energy, you see this suppression of the density of states near the Fermi level. And that's a reflection of the Coulombic interactions between the carriers, a Coulombic gap effect that is quite characteristic of such kind of localized systems with strong Coulombic interactions. And that is a factor that is also limiting the carrier conductivities, and it also limits the ability of electrons to delocalize, particularly electrons, of course, near the Fermi level. So we're starting to get a much better understanding also of the factors that limit conductivities in these conducting systems at high carrier concentrations. And with that, I want to conclude. I hope I've given you, this has to be, of course, a relatively fast-paced overview over how we understand charge transport in these organic semiconductors. And what's very clear is that there is this fascinating and maybe rather unique transport regime in which the structural, the charge, and also the spin dynamics are intimately coupled. I've shown you that in the molecular systems, we think that this transient delocalization framework is the most appropriate model to understand charge transport. We think the same is true also for polymer systems, and particularly for coupling of the charges motion along the backbone, which we are able to probe with our spin relaxation experiments. And then finally, on the conducting systems, I've shown you that this transient delocalization framework can also be applied there and helps us to understand what limits the conductivity in regimes where the carrier concentration approaches the molecular density. And with that, I want to acknowledge the people who've been involved in this work. In my group in Cambridge, in particular, Ian Jacobs, who's led the work on the conducting polymers. Guillaume Schweicher, who was responsible for the work on the mode-resolved electron-phonon coupling, and Sam Schott, who has been leading the work on our spin relaxation measurements. We've got some very productive relationships with chemists who provide us with very interesting materials. In particular, I want to acknowledge Ian McCullough at Oxford now, Martin Heaney at Imperial, J.K. Lee in Korea. Collaborations with Chris McNeil on the X-ray diffraction, and also with Joseph Stralska at Argonne, who also did some of the GWAX measurements that I showed. And then on the theory, very productive collaboration with Gabriele and Simone, with Vincent Lemour in David Beljon's group, Alexandre Vercoute in Jérôme Cornier's group did the thermal conductivity simulations, and then Eric McNellis in the group of Jairo Sinovo in Mainz, who is responsible for simulating some of the spin relaxation measurements that I showed. And with that, I want to thank you very much for your attention, and I'm very happy to answer any questions.
So thank you very much, Henning, for this fantastic talk covering so much exciting physics. So we have a number of questions. So my role will be to read them out for you. So the first question actually may be more related to some theoreticians here. On the slide devoted to Giannini's work, so you demonstrate a wave function that is delocalized in space and then more localized again. What about the coherence of the pure states described here by a wave function? Is it not yet spoiled by the interaction with phonons? So that's a question from Oleg, maybe more to Jochen. But,
well, Jochen, would you prefer to answer this?
Yeah, actually, I would not prefer to answer because I don't really know the question, the answer. But I'm trying. I'm trying to do that.
Okay, well, you're thinking, should I move to the second question so that we don't?
No. I think no, I can do that now.
Okay.
Yeah, so I don't think in the systems there is very much coherence, or if there is a lot of coherence, then it's probably not right. So, so essentially what these pictures show is just a one particle wave function that depends on time, and the time dependence comes from the classical motion of the nuclei. And this is really what you see here. So I'm not quite sure what is like what's suggested by spoiling the coherence of that state. Yeah, there is not much. So this electronic wave function just basically is coupled to the motion of the nuclei and the other way around.
All right, thank you, Jochen. I think we can continue the discussion during the coffee break.
During the coffee break or,
yes.
or on.
Yeah. So we have another question from Otello. What is the trade-off between processability and performance in strongly coupled polymers? So these are the rigid rod polymers that you showed with the double bonds.
Yes, that's a very good question. I mean, this is a solution processable system, PB/TTT, but it's on the verge of being practically, well, difficult to process. So these highly crystalline systems, they require often chlorinated solvents, so they're not easy to process. So we are we're properly approaching a limit of how much more we can improve crystallinity in these systems without sacrificing solubility. So that's an issue that we are facing. Yes.
But I think the question was on the polymers with the double bonds between the units.
Well, it's somewhat similar.
Somewhat similar, I guess. Yes.
The polymers with the double bonds. Let me just go back. They are also not so soluble. So you have to process them typically from a higher boiling point, chlorinated solvents. But of course, there's quite a lot of tuning you can do in terms of sidechain designs, and Ian McCullough's group has done that very elegantly. So you can engineer these polymers to be reasonably processable.
All right. So since you're talking about the
spin-coated drop cast films, so there's no problem doing that.
Mm. So you're talking about the side chains, and there is a follow-up question in a way. How much can one tell about, and this is a question from Abhishek, how much can one tell about the charge transport properties of conjugated polymers from structural measurements such as SACs or G-SACs? Can we say which polymer will have higher mobility out of multiple polymers with the same backbone, but different side chains based on SACs data, for instance?
Oh, well, I mean, that's a very good but difficult question. I mean, within a family of polymers, so if I, for example, took the PBTTT system and looked at different ways of growing the films and compare the structural quality of the films, then probably there would be a correlation between carrier mobility and quality of crystal quality, paracrystallinity, certainly. But if you look, for example, at this system here, this was at the time, it was a completely unexpected discovery. So we had a system that was very poorly crystalline, where you could hardly make out any crystalline diffractions. But nevertheless, it turned out to be much a better system than many of the crystalline systems that we've been working with. So it's quite complicated. What matters for charge transport is not just the quality of the crystalline order in the crystalline domain, which you probe with X-ray diffraction, but it's also important how well these domains are connected with tight chains between crystalline domains. You need to have chains that connect between these crystalline regions. And what matters also is what the conformation of those tight chains is. So it's not a direct correlation between an X-ray diffraction measurement and a prediction of carrier mobility.
All right, thank you very much, Henning. I think we will stop here the discussion. We'll continue, of course, at the coffee break. Thank you very much, Henning, for this fantastic contribution, and then we move on.